welcome you all in NPTEL online certificate course on mechatronics, this lecture on controllers. So, today we are going to talk about controllers, specifically I am going to talk about proportional controller, derivative controller and PID controller. Before we go into the controller, let us have a look at the concept of open loop versus closed loop control. Now, open loop control is often just a switch on off switch form of control. For example, if there is a room, okay, and you want to control the temperature of the room, you may switch on or switch off the heater of the room. Okay. For such a system, you have a plant or system is there, and you have a output, the desired output, the actual temperature, and input is actually the desired temperature basically, okay, in this case. Now, this desired temperature may be function of say how many heaters you have to switch on, of what wattage capacity and so on. Okay. The other type of control is the closed loop control, where a controller is used to compare continuously the output of a system with the required condition and convert the error into a control action designed to reduce the error. So, in open loop control system, we can see that there is no role of the actual output in deciding the input over here. There is no continuous feedback. Okay. Whereas, in case of closed loop controller, there is a provision of continuous feedback. So, this figure explains the concept of the closed loop control, where we have a plant or system. There is certain output from that plant and system, and there is a measurement device basically which measures this output, okay, and this measured output is compared with the reference input in a comparator, and then it is given to the control unit, where the control law is there. So, error is fed to that control unit, and the control unit gives the control action to the plant. Okay. So, these type of systems are basically called the closed loop system are called as the error driven system basically. So, it is the error which drives the system, and the intent of the such control system is to minimize that error. Okay. Now, this error might arise as a result of some change in the condition being controlled or the set value being changed. Now, the term direct digital control is used when the computer is there in the feedback loop. Okay. So, I will be discussing devoting one complete lecture on the digital control, that is the next lecture here. Okay. Now, there are many processes not only involves controlling some variables say temperature, but also involves in sequencing of the operations, for example, say washing machine, where one need to follow a definite sequence, okay, because say after cleaning only your drying operation could be there. Okay. So, here you need to have a certain sequencing also. Now, the sequence of operation might be clock based or event based or a combination of 2. Okay. So, clock based means it is dependent on time, or event based means it is dependent on an event to happen, that is if next task will be completing only if some earlier task has been completed. This is what we mean by the event based. Okay. Or you could have a combination of both the types. Okay. In many processes there can be a mixture of continuous as and the discrete control. Now, let us look at what happens if you have open loop and closed loop system and there is certain disturbance in it. Okay. So, a disturbance signal is an unwanted signal which affects the output signal of a system. Okay. And with feedback there is a reduction of the effect of disturbance signal on the system. Now, let us first look at open loop system with the disturbance or open loop system. Suppose you have a input given by Rs over here, there is a block with the transfer function G1s. You have output here given by Xs, and here there is another block G2 whose transfer function is given by G2s, and here in between both these say there is a disturbance ds. Okay. This is being summed up, this disturbance is being added up in the signal which is coming from G1s. So, now here we can see that what is my Xs. Okay. So, Xs is basically what it is G1 times Rs. Okay. G1 times Rs, this one, and then ds is being added into it. So, this is the net value of the signal, this one over here, and then this multiplied with G2s, and that will be giving me the Xs. Okay. Or if I multiply this one inside, so what I have is G1s Rs G2s plus ds G2s. Okay. So, you can see that this is the term actually which is contributing because of the disturbance. Okay. So, this is the contribution to output because of disturbance. Okay. Now, let us look at a closed loop system, okay, with a disturbance. Okay. So, again here I have got the first block with transfer function G1s, second block with transfer function G2s, and in between I have got the disturbance ds over here. Here is the Xs, and this is the feedback, and there is a transfer function in the feedback path, that is say Hs. Okay. And then this is sent for comparing with the reference input, say Rs. Okay. Here you see what is my Xs. Xs is basically G2s times whatever is coming over here, and what is coming over here is this thing basically. So, you have Rs minus Hs Xs is over here. Okay. And then so here you get Rs minus what Xs Hs, this is here, and that multiplied with G1s. So, the Rs minus Hs Xs. Okay. This is there, this multiplied with G1s. Okay. So, this is coming over here, and now I add up ds over here. Okay. And this whole being multiplied with G2s will be giving me the Xs. Okay. Now, I can simplify this, I can take this Xs out left hand side, okay, and I can simplify this. So, this is what I am going to get. Okay. So, now in this case you can see that this term actually is as a result of the disturbance ds, and if I compare this with that of the open loop case. Okay. So, here this was dsG2s, okay, and here you see that this is dsG2s divided by 1 plus G1s, G2s and Hs. So, basically the effect of disturbance is reduced by this factor in case of the closed loop control system. So, we can see that the closed loop control system is able to reduce the disturbance. There are the term commonly used with closed loop controllers is a lag. Lag is a very common term which is used, and it is time required for the system to make the necessary responses. Okay. For example, say in a central heating system, a lag will occur between the room temperature falling below the required temperature and the control system responding and switching on the heater to restore the room temperature. Okay. So, in this process actually does not take place immediately. So, there is going to be a certain amount of lag in it. Okay. Okay. Next thing is let us see as the steady state error. Okay. So, steady state error, as the name indicates, you can see that the error which occurs when there is a steady state. Okay. So, it is actually the difference between the desired set value input and the output after all transients have died away. So, actually this is what we say about steady state, that is if your output is I am plotting output versus time. So, if your all transients have died away, then this state is basically what we call it as the transient state, and this state is actually the steady state. Okay. So, when and this is the transient. So, when all the transients have died away, that state is basically what we call it as the steady state, and it is measure of the accuracy of the control system in tracking the set value input. Okay. So, suppose I have got a control system here with the reference input Rs and output Xs, say it is a unity feedback control system. So, you have unity feedback here, and the transfer function of the feed forward path is say Gs over here, and here is the error. So, error will be basically the input minus output. Okay. So, for this system, as we have seen earlier, the transfer function is actually Xs by Rs is equal to Gs by 1 plus Gs. Okay. The general expression is actually Gs by 1 plus Gs Hs, where Hs is the feedback, but since we are talking about the unity feedback here, so it is only 1 plus Gs. Now, if I look at what is the value of the error, so the error is actually the input, that is Rs minus the output Xs. Okay. So, this is Rs, and Xs I can write from this expression as Gs Rs divided by 1 plus Gs. Now, if I take Rs outside, then what I will have is 1 plus Gs minus Gs divided by 1 plus Gs. So, this is basically 1 plus Gs into Rs. Okay. So, this is the error. Now, if we want to find out the steady state error in the time domain basically. Okay. So, what we can do is that we can use the final value theorem. Okay. And this final value theorem basically says that the steady state error is going to be equal to the that is the Et error when t is tending to infinity. Okay. So, the limit value of that, and this is what you have to do is that you have to take the limit of s times Es with s tending to 0. Okay. So, this way I can substitute Es over here, and I can find out the steady state error. Okay. Next, let us look at the various type of control modes. Okay. So, now here the use of these control modes is basically to work for the two things actually rather two it is the three things, that is the any control system is designed to look after the three aspects. One is to improve the transient behavior, okay, transient behavior. The second thing is to reduce the steady state error, and third thing is about the stability, okay, to make the system stable. So, in any control system actually we look at improving upon these three factors. So, the control modes for industrial analog controllers, various possibilities are the two step mode, or what we call it as the on off controller. Then we have the proportional mode, proportional controller, derivative mode, derivative controller, integral mode or integral controller, and combination of modes, that is we could also have the combination of these, that is the proportional derivative, proportional integral, as well as the proportional integral derivative. So, these could be the three combinations possible. Okay. We can these can also be classified based on the power used as hydraulic controller, pneumatic controller, or electronic controller. Now, let us look at first of all the two step mode. Okay. In the two step mode, the controller is essentially just a switch which is activated by the error signal and supplies just an on off correcting signal basically. Okay. And the two step control action tend to be used where changes are taking place very slowly. Okay. That is with a process with a large capacitance. The two step control is thus not very precise, but it does involve simple devices and thus fairly cheap. For example, our bimetallic thermostat. So, here you can see that say we have the heater supply, its on condition is this one and this one is the off condition, and the controller switch point is this one. So, basically you can see that here say the controller could be on say at this position if your temperature is falling. Okay. So, if your temperature is falling, okay, say as you can see over here. So, you could switch on the heater supply, then temperature, then after some time the temperature starts increasing. So, you can switch off the heater supply over here. Okay. And again at this position when the temperature start falling, okay, then again you may like to switch on the heater, okay, so that again the after some time the temperature starts increasing. So, this is basically what is this on off control is, and here actually as I was telling you there is a dead band basically, okay, that is after switching on it takes some time, it takes such time for the action to take place. Next is the proportional mode. Okay. With the proportional mode, the size of the controller output is proportional to the size of the error. Okay. So, the bigger the error, the bigger the output from the controller is. Okay. So, in this case the controller output is actually KPE, and if your error is more, your controller output is more actually. Okay. So, that is there, and if you want to reduce the error basically, so as you can see from this equation, the Kp value has to be increased. Okay. But you cannot go for increasing the Kp value to any limit, because a very high value of Kp makes your system unstable, and that is also not good for a system. As I discussed with you, the three essential criteria which we are looking in any control system is the transient behavior, steady state error, and the stability. So, naturally we would not like to go for a very high value of Kp. Okay. It is a constant basically called proportionality or proportional gain rather. Okay. So, if I take the Laplace transform for this, this is going to be Kp times Es, and the Kp is the transfer function of the controller. With the proportional control, we have a gain element with transfer function Kp in series with a forward path element Gs. Okay. So, as you can see here, so this is my proportional controller over here. So, in this case we have we can see that my error is going to be Rs by 1 plus Kp times Gs. So, if I am looking for the steady state error, this is going to be limit s tending to 0 of SES, or this is 1 by 1 plus Kp into Gs. Okay. If I am taking Rs is equal to 1 by S as the input, that is I am taking the step function as the input. So, this is going to be the steady state error. So, what does this means? This means that your system which is proportional control, you are always going to have a steady state error. Okay. And with the increase in value of Kp, you can reduce this steady state error to some extent, but you cannot eliminate it to 0. Okay. For eliminating it to 0, we need to put up or combine this controller along with the another controller, that is the integral control, which I will be discussing with you in the coming slides. Now, next let us look at the derivative mode. Okay. The derivative mode produces a control action that is proportional to the rate at which the error is changing. Okay. That is, your controller output is equal to Kd times dE by dt, that is it is proportional to dE by dt, and here Kd is the constant of proportionality. Okay. And here, so when there is a sudden change in the error signal, the controller gives a larger correcting signal. Okay. When there is a gradual change, only a small correcting signal is produced. This is what is meant by the derivative control. So, the transfer function, if I am looking at it for this, so it is going to be Kd times SES. Okay. And this is going to be there. Okay. Now, with derivative control, as the error signals begin to change, there is a large controller output, and it is proportional to rate of change of error signal and not its value. Okay. And it is some form of what we call it as the anticipatory control, that is one which anticipates what is going to happen there in the future. Okay. So, here here you can see that if there is a constant rate of change of error with time, okay, as you can see by the constant slope for this one. So, you are going to have a control action like this. Okay. So, as the controller output that result when there is a constant rate of change of error signal with time, and the controller output is constant because the rate of change is constant. Okay, and that occurs immediately, the deviation occurs over here. Now, the derivative controller do not respond to the steady state error signal. Why? Because you see, if a steady state error signal that value is going to be there, then d by dt will be 0, because your error has become constant in the steady state. Okay. So, in that case you are not going to have any control action. Okay. So, with the steady state error, the rate of change of error with time is 0, and because of this the derivative control is always combined with the proportional control. So, that when the steady state error is reached, the proportional control takes over. Okay. So, usually the role of the derivative control is to improve the transient behavior. Okay. And for the steady state portion, the proportional control usually takes over. So, the proportional part gives a response to all error signal including the steady signal, while the derivative part responds to the rate of change basically. Okay. And that is what is happening in the transient zone. Now, this derivative action can also be a problem if the measurement of the process variable gives a noisy signal. Okay. But in a mechatronic system, as I said, we have the sensors to measure the signal values. Okay. And if there is a noisy signal, then the derivative action can give you a problem. Okay. The rapid fluctuation of noise resulting in output, which will be seen by the controller as a rapid change in the error. Okay. And so, give rise to the significant output from the controller. Next, let us look at the integral mode. Now, the integral mode is of control is one where the rate of change of control output is proportional to the input error signal. So, basically this is d I by dt is proportional to E here. Okay. And this k I is the constant of proportionality and has the unit of 1 by s. Integrating the above equation actually gives you that is the integration of di from I 0 to I out is 0 to integration from 0 to t k I into E dt. So, you have I out minus I 0 is integral 0 to t k I E dt, and here I 0 is the controller output at 0 time basically, and I out is the output at time t, and the transfer function is obtained by taking the Laplace of this. So, you have I out s minus I 0 in the Laplace domain, and this will be k I E s divided by s basically. Okay. So, so the transfer function for this controller is going to be actually k I by s. The action of an integral control when there is a constant error input to the controller is like this here. So, if you have a constant input error here, then the controller output is going to be like this. Okay. So, this control is very much useful, as I indicated to you earlier. If there is a steady state error or a constant error, then the controller this type of controller is used. then we could have, so we have seen the characteristic of the proportional control, we have seen the characteristic of the derivative control, we have seen the characteristic of the integral control. Okay. So, by combining these, okay, we could get a combined characteristic of this controller. Okay. So, there are the various combination of modes possible. So, say this one is proportional plus derivative mode, that is what we call it as the PD controller. Then we have proportional plus integral control, or what we call as the PI controller, and we have proportional plus integral plus derivative, or what we call it as the PID controller. Now, let us look at the first one, proportional and derivative control. Okay. So, the derivative control is never used alone, that I have explained to earlier also. Why? Because it is not capable of giving an output when there is a steady state error signal is there. Okay. And the control action will be 0 in case of steady state error. Okay. So, that is why it is usually used in combination with the proportional control. Okay. So, the controller output here is actually Kp times E plus Kd times dE by dt. So, this part is basically this part is actually your derivative control, and this part is actually your proportional control. That is why this is called as the PD controller. So, Kp is the proportionality constant and Kd is the derivative constant, and dE by dt is the rate of change of error. So, the system as a transfer function we can write in terms of the S domain. So, Kp Es plus Kd S Es, and so the transfer function for this controller is Kp plus Kd S. Okay. And this is often written in another form. I can take Kd out here. So, what I get is S plus 1 by Td, and this Td is actually Kd by Kp, and this is called as the derivative time constant. The controller output can vary when there is a constantly changing error. Okay. And there is an initial quick change in the controller output because of the derivative action, followed by gradual change due to the proportional action. Okay. So, this form of control can thus deal with fast process changes. So, this is how it is. So, you have the error over here, and here is the constant over error over here. Okay. So, you have the derivative element in this zone, and you have the proportional element over here. Now, let us look at the proportional integral control. Okay. The integral mode of control is not usually used alone, but it is frequently used in conjunction with the proportional mode, and as I said, it is usually used to reduce the steady state error. When integral action is added to a proportional control system, the controller output is given by Kp times E plus Ki times integral of I e dt. So, this is actually your integral control, and this is your proportional control. So, that is why this is called as the Pi control over here. Okay. So, the Kp is the proportional constant, control constant, and Ki is the integral constant, control constant, and E is the error. Now, the transfer function for this is Kp plus Ki by S, okay, or I can take Kp by S over here. So, here it is S plus 1 by Ti, and Ti is Kp by Ki is the integral time constant. Okay. So, here you can see that your error, if it is a constant over a error over here. Okay. So, this constant error is taken care by the integral control action over here. So, this one portion basically corresponds to the proportional element, and this one corresponds to the integral element. next is the combination of all three, that is proportional, integral and derivative controller, which is a very popular controller and it is mostly used in the industry. Okay. So, the PID controller, it is the combination of all the three modes of control, that is the proportional, integral and derivative control. Okay. And it is also known as the 3-mode controller or the PID controller. The equation deriving its action can be written as Kp times E plus Ki E dt plus Kd d by dt. So, this is basically your derivative control, this is your integral control and this one is your proportional control. Okay. And these terms are they have the usual meaning which I have discussed earlier. So, if I take the Laplace transform for that, the controller output is this one basically, for the proportional one, this is for the integral one and this is for the derivative one. So, the transfer function for PID controller is actually Kpe plus Kp plus Ki by S plus S Kd. Okay. Or I can write it in terms of this one also. Now, how this these controller could be actually implemented in a discrete circuit. Okay. So, we can physically realize these type of controller with the help of operational amplifier. Okay. So, I am just discussing this for the PID circuit. You can refer standard text for the other type of implementation for the other type of circuit, okay, other type of control actions. Okay. So, the 3-mode controller can be produced with a single op-amp or operational amplifier. Okay. So, here you can see that this is my op-amp, okay, and here in the feedback path of the op-amp, okay, I have a resistor and I have a capacitor here, and here I have a resistor over here, and here in the inverted input one I have a resistor and I have a capacitor over here. Okay. And the non-inverting terminal is grounded over here, I get output here and this is the error one. Now, I am not deriving this, okay. We have already seen the op-amp and its working, and op-amp as the signal conditioner we have already seen, and for this case actually the proportional constant is actually R1 divided by R plus RD. Okay. So, R1 plus R plus RD is there, the derivative constant is RD/CD and the integral constant is 1 by R1 C1. Okay. So, that is there. Okay. So, or CI/RI. So, corresponding to the integral one. Okay. So, this way we can physically implement these controller. Okay. So, these are the references by Bolton, and you can refer our book on intelligent mechatronic system also. Thank you.